Assalamu alaikum warahmatullah. So this is your second lecture on on linear algebra. So this is lecture 2, and this is about the geometry of linear algebra. Okay. So in the first class, I told you about um, the usefulness of using the geometric pictures of linear algebra. It is for a better understanding of the operations that you are doing on different sort of data, right? So you would see that how we can use geometry to have a better understanding of what this linear algebra does on a particular data set. Okay. So, for example, take two equations of a single linear system. Okay. So, for example, let's take two equations. Suppose this is one and this is the other one of them. Okay. So, this system of equation can be written in a matrix form. The matrix form would be, I think you're familiar with this. It should be 2, -1, then -1, +2 multiplied with the variable vector, and this is the solution set. Now, frequently I would be working with this sort of linear systems, and I would call this matrix A. That means the coefficient matrix A. The variable vector, I would call it as X, and this solution set, I would call it as B. So the whole thing can be written as AX equals to B. Okay. Now, if you take one one equation at a time, then if you want to picturize that equation on a 2D plane, as this is a this equation is a part of a 2D coordinate system. So let's say you have a 2D coordinate system. Sorry. And you want to draw this first equation here. So you want to draw that first equation here. Now, how do you draw it? So to draw it, you might know this from your previous level of studies, that you have to assume two values for x and y so that it becomes 0. Okay. For example, if x has the value 1 and y has the value 2, then you will get this equation, right? Similarly, if x has the value 2 and y has the value 4, then you will get this equation as well. And taking all those points here, or plotting all those points here, you will get the first equation, right? So if you plot all these points, I think you will get points like this, It might not be accurate, but it's just an idea that you will get a point like this. Okay, then like it will go through the origin. Okay, so if you combine all these points, you will get what? You will get a straight line. Right, you'll get a straight line. So 2x minus y equals to 0. So I think this part is clear, that if you plot all the points of the first equation, you will get a straight line. So what is the picture of this first equation? It is a straight line, okay, that goes through the origin. Now, similarly, if you plot all the points of the second equation, then you will get another straight line as well, okay. So maybe, or suppose this is the straight line for minus x plus 2y equals to 3, okay. And the point where they intersect is this point. So this point is, let's say 1, 2. This is the solution. So this is the complete picture for a 2D coordinate. For a linear system of equations which has two equations in this case. Okay. So this is the complete picture of this linear system of equations, where you get to draw individual straight lines for the two equations and get one intersection point which is their solution. Okay. Now this, in this particular example, you have worked with one particular equation, or for this system that is written here, you have worked at the row level. Okay, you have taken one row and you have plotted that row, then you have taken the second row and you have plotted that row, and you have got a picture. You have got a picture here which actually represents that particular system of equation, right? So as you have worked with, or as you have worked in the row level, so this picture is called the row picture. Okay, the row picture of a linear system of equation. Okay, so there are two takeaways from this part of the lecture, that the picture of a 2D equation is a straight line. Okay, can you get this point? Let's say this point is negative 2, 2. Can you get to this point with this equation? The answer is no, because the equation can only move through this through this straight line, right? For example, you can easily get minus, let's say minus 2, minus 4. Let's say this point is minus 2, minus 4. So if my question was, can you get minus 2, minus 4 with the first equation? The answer is yes, because it goes through this point. The straight line that represents this equation goes through this point. Okay. So in the previous lecture, we talked about span, right? Span means all the points, all the data points that you can achieve or you can explore with a particular equation, okay, or a particular vector. Maybe we'll get to vector later part of this lecture, but for the time being, think about this equation. What points can you get with this system of equation? You can get only the points where y coordinates are twice as big or twice as less as the x coordinates, right? So this is the span of this equation the span of this equation is basically this straight line. Okay. And the second takeaway here is that if you work at the row level, you will get the row picture of any linear system of equation. Okay. So I think this row picture concept is clear. Now we would work at the column level. Okay. So let's write that system of equation again. 2, -1, -1 and 2 is xy 0, 3. Now what we would do is we would work at the column level. So we saw one approach of matrix vector multiplication in the previous class. That particular approach is that you take one vector, so you take one element of the vector, you multiply with the first column, you take the second element and you multiply with the second column. Okay. So that approach would be x multiplied by 2, -1 plus y minus 1, 2 equals to 0, 3. Right. Now let's draw these vectors on the 2D coordinate system. As there are two elements, the system is a 2D coordinate system. Okay. So this is x, y. Let's say this is the first, this is the first vector, which is 2, -1. This might not be accurate. Okay. Or let's do it more accurately. Let's say this is 2, this is -1. So this is your first vector, which is 2 and a -1, and this is your second vector, -1 and 2. So this is your second vector, which is -1 and 2. Okay. Now I have to find one combination of x and y so that it gives me this this result or this solution 0, 3. So what should be that particular combination? Why not the correct combination, which is, we already know, 1, 2. Okay. So if you place 1 here and 2 here, then if you do vector addition, okay, so the picture would be 1, 2, -1 plus 2, -1 and 2 equals to 0, 3. Then this is basically vector addition, and what you would do is that you take one of these vectors, then two of these vectors. So this is the vector, and you have to take two of these vectors from the tip of this vector. We know how to add two vectors from the previous class, right? You take one vector, and at the tip of that vector, draw the other vector, and you will get the resultant vector from the origin. Okay, so this is, let's say this is 1 of -1, 2, and this is 2 of -1, 2. Okay, so this is, let's say, this particular vector is twice of the minus 1 2. So the resultant vector is from the origin to the tip of the other vector, right? So this, what is this point? This point is, let's say, 0 3, which is the solution. Okay, so what have you done here? So this is your B vector, which is 0 3. So what have you done here? Why this is B? Because I told you that we would work with this system of equation with this notation Ax equals to B. So the solution is B. Okay, so what have you done here? As I was saying, that you have worked in the column level, right? You have worked with individual columns, right? You have worked with individual columns, so that's why this picture right here is called the column picture, and this is mostly important to us. Okay, so throughout the course we work with the column picture. Why? We'll know later. Okay, so this was a 2D coordinate system, which is very easy to interpret, but let's switch it to 3 equations and 3 unknowns. Okay, let's take 3 equations with 3 unknowns. So take a random system of equation. Let's say 2x minus y equals to 0. Okay, I would modify it a little bit. 2x minus y equals to 0. Then minus x plus 2y minus z equals to minus 1, and minus 3y then plus 4z equals to, let's say, 4. Okay, and if I want to write this system of equation into matrix form, it would be written as 2, a negative 1 and a 0, minus 1 and a positive 2 and a negative 1, and 0 and negative 3 and a positive 4. And this is the variable matrix or vector x, y, z, and this is the solution set 0, minus 1 and 4. So this is A, this is x, this is B. Okay, now if I try to draw it, what would be the picture? So it is quite difficult to draw a 3D coordinate system on a 2D plane, because the plane on which I'm writing is basically a 2D plane, right? So let's try. So this is a 3D coordinate system. Okay, let's make it bigger because we'll need it. So this is one coordinate, this is the second one, this is, let's say, this is the third one. Okay, so let's say this is x, this is y, this is z. Now if you try to draw the row picture first, then first try to draw this second equation. So the second equation has all the 3 components, right? So that's why I have chosen this one first. Now if you take different values for this x, y, and z, you will see that so in the previous example where you tried to draw a equation with two unknowns, you got a straight line for the row picture, right? But here you will see, if you try to draw this this equation, you try to draw this equation on this 3D coordinate system. So if you try to draw this system of equation, this one particular equation, you'll get many points like 1, 0, 0, then 0, 0, 1, then 0, negative half, 0, points like this. So if you draw this point, if you plot all these points here, what you will get is a plane. Okay, you will get a plane on this 3D coordinate system. Okay, which will have all the three components. Okay, so the row picture of this particular equation would be a plane through the origin in this 3D coordinate system. Okay, now you can get a visual representation if you try to solve this equation on a website called Wolfram Alpha. Okay, Wolfram Alpha. If you go to this website, and if you try to find the solution for this particular equation, you will see the visual representation of having a plane through the origin on a 3D coordinate system for this particular equation. Okay, so similarly you will get another plane for this equation. So let's say this is that plane. Let's say this is that plane. Maybe it is not accurate. So if two different planes, so suppose you do not have this equation with you, you only have these two equations. So if two planes actually meet each other on a 3D coordinate system, what you will get? Okay, what if two paper from your notebook meet? Okay, what should be the picture of the solution? The picture, if two planes meet each other, the picture would be a straight line, right? So you can like think of your own that if two papers are basically two planes, right? If two papers meet each other, then you will get a straight line, right? And that is their solution. Okay, so we have got one insight that on a 3D plane, if two planes meet each other, you will get a solution of straight line. Okay, or you will get an arrow, you will get an array of points where that array of points will create a straight line, right? And if another plane for this equation meet those three planes, then the solution will no longer be a straight line. The solution would be a single point, as you can see here. Okay, so you will get one single point if you have two or three planes meeting each other on a 3D plane. Okay, so the picture is clear. So there are some takeaways from this row picture of a 3D or 3D coordinate system. So the first one is, for every particular equation you get one plane in the 3D coordinate system. If two planes meet each other, then you will get a straight line as a solution. If three planes meet each other, you will get one single point as a solution, right? So this is the row picture. Now the column picture of this, so you have worked at the row level for this 3D coordinate system. Now you'll work with the column level. Okay, so the column picture would be, or you can express it as x. So x into the first column, y into the second column, z into the third column. Okay, so x into 2, negative 1, 0, plus y into negative 1, 2, minus 3, plus z into 0, negative 1, and 4. So, and the solution B is basically 0, minus 1, 4. Okay. So this is one equation. So what this equation is asking is that you have to find one particular combination of these three components, x, y, and z, so that you produce the right combination here. That means 0, minus 1, and 4, right? So look at it carefully. If you take, okay, let's draw the column picture. Okay, so this is the coordinate system. So this is your column picture. So if you draw the first, so let's say this is x, this is y, this is z. So this is 2, this is negative y, and it is 0. So let's say this is the first vector, 2, minus 1, 0. So the second one is minus 1, minus 2, minus 3. So minus 1 this side, minus 2 this side. Sorry, minus 1, 2, then minus 3. So let's say this is at this point. It might not be accurate. Okay. So because it is very difficult to draw a 3D coordinate system on a 2D plane. And the last one is 0, negative 1, and 4. So 0, negative 1, and 4. So let's say it is this one. So this is 0, negative 1, and 4. This is negative 1, 2, minus 3. Now you have to find one combination of one particular combination of x, y, and z, so that you get this solution. So what should be the solution? One solution can be x is 0, y is 0, and z is 1, right? If you take none of this vector, if you take none of this vector, and if you take one of this vector, then you'll get this solution. Okay, so this is the solution for B if you take one of this vector. So this is the column picture. Imagine if you have a different right hand side. Let's say if you have another right hand side, not this one, let's say you have this right hand side. 0, -1 and 4. Okay, I'm sorry, it should be 1, 1 and -3. So this is your solution set. How do you get this? So I've removed the previous one because I want to take a special right hand side or a special solution. The special solution here is, or the solution here is, if you take one of the first vector, one of the second vector and none of the third vector, then if you simply add these two vectors, you will get this one. Okay, so this is, so in that case the picture would be okay, I have to draw it again. So let's say this is x, so this is the first vector, the first one. This is the second vector, let's say this is the second one, and this is the third vector, third one. So if you add one of the first two vectors, so from the tip of the first vector, let's draw the second vector. Let's say it comes here, and if you add these two lines, then maybe this is the solution. Okay, as I told you, this is very difficult to draw a 3D coordinate system or 3D vectors on a 2D plane, but suppose this is the right procedure, or this is the approach that you should use while drawing the column picture. Okay, so so this is the solution B. Okay, so what we have learned at this point is that we have solved two different B's for one particular combination of the linear system, right? So the question is, the big question is, can I solve Ax equals to B? So we have solved Ax equals to B for two different B's here, okay? And that two different B's actually lead to two different points on this 3D coordinate system. The first point is this, and the second point is this. Maybe the points are not accurate, but this is just the idea. So my question is, can you solve every B for Ax equals to B? That means if I take any point at this 3D coordinate system, maybe this point, maybe that point, maybe that point, maybe that point, then can I solve it with this Ax equals to B? This is the question here. Okay. And I think you already know the answer. The answer actually lies here. The answer lies here. So I told you in the previous class that this is the linear combination of vectors, right? X, Y, and Z actually points the particular portion of linear combination, that how many of the first vector, how many of the second vector, or how many of the third vector should be combined each other to get the right hand side, right? So this is the question. So in linear algebra, so the question that I have asked here, it should be rephrased from the point or from the perspective of linear algebra, and the question in the linear algebra should be, do the linear combination of these columns, do the linear combinations of these columns actually fill or reach all the points of 3D space? Or similarly, it can be asked, do the linear combination of these columns fill the whole 3D space? This is the question. Okay. So the question should be, do the linear combination of the columns fill the whole 3D space? Which columns? These columns. Okay. So for this particular matrix, or this for this particular columns, the answer is yes. The answer is it can fill the whole 3D space, because this particular matrix is an independent matrix, or the columns are independent of each other. That means this particular matrix is invertible. This is not a singular matrix. This is a non-singular matrix. That means it has the ability, or it has the power to explore through the whole 3D space. Okay. For certain matrices, the answer could be no. Okay. When it could go wrong? So that means in which cases I cannot generate a random B? If all the three vectors actually lie on the same plane. As you saw in the row picture, that you got three different planes for three different equations. That's why, as you have got three different planes on a 3D coordinate system, that's why you can reach every point on that particular 3D system. Okay. If you could get two planes on this 3D system, you could not reach out to all the points on this particular 3D system. Okay. For example, if you had a matrix like this, if the matrix was like this, 2, -1 and 0, -1, 2, -3, and let's say the third column is same as the first column. Okay. In that case, you could get one plane from this column, one plane from this column, one plane from this column, but you could not get a different plane for this column. So you cannot reach out to all the points on that particular 3D system. Okay. So similarly, if the first column or the third column was a scalar combination or a scalar multiplication of the first column, let's say this is 4, -2 and 0, so this is just a scalar multiplication of the first column, then you cannot actually get anything, or you do not get anything new from their combination. That means you cannot generate any random vector B. Okay. Okay. So in that case, this matrix is not invertible. This is a singular matrix. The determinant is 0. So that's why you cannot get the whole 3D space with the help of these 3 columns. Okay. Now, think about 9 dimensions. So we have worked with 3 dimensions here, right? Think about 9 dimensions. Let's say we have a vector of 9 components. We have a vector of 9 components with 9 equations and 9 unknowns. So if we have a vector with 9 columns, can we hit all the vectors B in that particular dimension? I cannot I cannot draw the picture here because it is impossible to actually draw a 9-dimensional system on a 2D plane. But like you can use your think process. Imagine you have 9 equations. So we had 3 equations with 3 unknowns in this case. Imagine we have 9 equations with 9 unknowns. So if we have a vector with 9 columns, can we hit all the vectors B? The answer is sometimes yes, sometimes no. Let's say you have different columns. All the columns are independent of each other for that 9-dimensional matrix. Then you can get any B on that particular system. But let's say the 8th column is same as the 9th column, then actually you cannot reach out to all the points of that plane. You cannot reach out to the, let's say, 9th, or cannot reach out to the points that are in the 9th dimension. Okay, because you have the data points that allow you to move throughout the 8-dimensional data points, right? So what you will get is that you will get 8D plane. You will get an 8D plane on a 9-dimensional coordinate system. On a 9-dimensional coordinate system. Okay. So if I give you any particular system of equation, let's say 2x plus y equals to 3, then x minus 2y equals to minus 1. If I ask you to find out the row picture and column picture, I think you'll be able to do this after this lecture. Okay. So see you in the next discussion session, inshallah. So I know you'll have a lot of questions, so no worries. I'll upload this video on YouTube, so ask there or just save it for yourself and ask me in the discussion session. Okay. So yeah, thank you for your patience. Assalamu alaikum.